our bell ringer statements today were that unlike sound, light is able to travel in a vacuum, not an actual vacuum you use to clean your house, but empty space. So if you would agree, and those who would disagree, okay, so we'll be paying attention to see what the answer to that is. And then the other one was that all light travels at the same speed. Agree? And disagree.
Difficult, huh?
Okay, so be listening for that too. On top of that, you have a few objectives. Folks, attention. You have a few objectives for today. Differentiate between sound waves and light waves. That just means be able to tell me the differences between them. Distinguish between types of electromagnetic radiation. So how can you tell what type of electromagnetic radiation you're looking at? And then finally, describe how light is affected when it strikes objects. There's about 4 different ways we're going to discuss. Okay? Just like sound, light is energy. Energy being carried by waves. But they're not the exact same waves that carry sound. Things are a little bit different. Okay? Light is an electromagnetic wave. So it's not a longitudinal wave. It's not made from vibrations. Okay? It is a transverse wave where matter moves perpendicular to the direction of the wave movement. So if you remember yesterday when we drew the waves, we said the matter moves side to side and the waves move side to side. In this case, matter is caused to move up and down, but the waves move side to side. So they are perpendicular to each other. It's a different type of wave. Additionally, electromagnetic waves can travel without matter, which we know from our notes on sound cannot do. Sound requires matter to move. Light does not. Light can move through matter, but it doesn't require matter to move. It can also move not in matter. Another difference is that light is much faster than sound. Okay? Both of them are pretty fast, which you know from the fact that you're hearing me almost immediately after I speak. But light is even faster than sound. It travels at about 3 million meters per second.
Can you go back one, please?
Mm-hmm.
Wait, don't mind.
When light enters a material, that material is going to slow light down. As you can imagine, right? You add stuff to move through, all of a sudden it's a little harder to move through. It's going to be slower. Not a ton slower, but a little bit slower, and each material is going to change it a different amount. If you want to see a small table with some common speeds of light in some common materials, there's a nice one in your book that you can check out. Light is not the only type of electromagnetic wave or electromagnetic radiation that there is in the world. Light is a very small part of a larger spectrum, and we're just going to take a couple of moments to talk about that spectrum. I'm not going to go into huge amounts of detail, okay? We classify the electromagnetic spectrum into types based on their wavelength. So when I said you'll be able to differentiate between types of electromagnetic radiation, that means that you'll be able to tell that they are different based on their wavelength. And here is a table that shows the wavelengths and the type of radiation that goes with them. It's a little hard to read on the screen. I'm going to read it to you. Okay. So the very first type up at the top is radio waves. Okay. Radio waves, like you might use to listen to the radio, but also the type that carry long-distance phone calls, have wavelengths greater than 0.3 meters. So if it is a type of electromagnetic radiation and the wavelength is greater than 0.3 meters, then we would say it's a radio wave. The next type down is microwaves. Okay, so we're going in order of decreasing wavelengths, so these wavelengths are getting smaller. Anything between 0.3 meters and 0.001 meters is a microwave. Okay, we call the appliance microwave a microwave because it is using microwaves to heat your food. So that's a use for them that you would encounter. Then underneath that, we have infrared, which is INFRARED. Infrared, okay? And that's wavelengths between 0.001 meters and 700 nanometers. Nanometers are significantly smaller than meters, so even though that number looks bigger, it is a smaller wavelength. Okay. Infrared, if you've ever seen the sort of like heat detecting cameras, they are detecting infrared waves, so you can use them to see where people are losing heat from their houses. Then we have visible light right here in the center. That's 700 nanometers to 400 nanometers in length. So you can see this is a very small portion of the electromagnetic spectrum. To us, it's a very important part because it's the portion that we can see, but it is a very small part. Underneath that, we have ultraviolet, spelled like the words ultra and violet put together, from 400 nanometers to 10 nanometers, so we're getting pretty small now. Okay. Ultraviolet light is sometimes used to sanitize things, okay, because it can kill bacteria and viruses. Okay. Then, if we go down even smaller, we get X-rays, which are 10 nanometers to 0.01 nanometers. I'm sure you know what we use X-rays for, but they're used for imaging inside your body. Okay. And then we have gamma rays, which are anything less than 0.01 nanometers. And I cannot remember off the top of my head what we use gamma rays for. It's not a super common thing, but they are useful. Okay. This is all the types of electromagnetic radiation, and we tell them apart by looking at their wavelength. All right. That's 2 objectives down, telling the difference between light and sound waves and telling apart the waves of electromagnetic radiation. Now we're going to talk about what happens when light hits an object. Okay, there's going to be about 4 different things we're going to discuss. The first thing that can happen is transmission. This just means that light is allowed to pass through an object. So when light is allowed to pass through an object, it's said to transmit light. Okay? These objects are clear, okay? And we describe them as being transparent if they allow all light to pass through them, like our windows. And they're said to be translucent if they only allow some light to pass through them and kind of scatter it to create a fuzzy image, like looking through wax paper or a frosted glass window. Another thing that can happen is that light can be absorbed. Okay? It can be absorbed. That means taken in. So objects, when light strikes them, take in some of that light, okay? And sometimes it gets turned into thermal energy, which is why you warm up when you get into the sun. Some objects absorb more light than others, which is why certain colors of clothing you will get warmer in the sun faster because they are absorbing more of that light than other objects. Next up, we have reflection. When light strikes an object and it bounces back, it's said to be reflected. Now, it's important to know that all objects, at least all the ones you can see with your eyes, reflect at least some portion of the light that strikes them. Okay? Light reflecting off objects into our eyes is what allows us to see them. If no light reflected off of this object, I would not know that it was here because there would be no light getting to my eyes telling me there's an object here. Okay? The exception to this is, of course, objects that are 100% black are absorbing all light. So when we see black, what we're actually seeing is an absence of light. Okay, but none of your clothing is 100% black. Even these desks are somewhat reflective with a coating on them, right? So we can still see that they're here. If you want to see what 100% black looks like, you can look up images of things painted with the color Vanta black, which has a really high absorption rate, and it almost appears that there's just a hole there shaped like that object, okay? Because that light is being taken in. The other exception is objects that emit light. So I don't see the flame on a candle because light is being reflected from the flame. I see the flame on the candle because the flame on the candle is producing light that I see. Okay? But aside from that, all objects have to reflect light in order to be visible. Objects that reflect or absorb all light that strikes them and they don't allow any of it to pass through them are said to be opaque. While all objects reflect light, it's not all the same. One thing that is true about all reflection, though, is that if you shine light on a surface at an angle, it will be reflected off of that surface at the same angle. So that would just look like this. If you shine light in at a 45-degree angle, light will bounce out at a 45-degree angle. Okay. The difference part comes in the type of reflection that we have. Okay. Regular reflection is when all light is reflected at the same angle in the same direction and reaches your eyes in an organized pattern and therefore produces an image. This is the type of reflection you see in a mirror or in a piece of glass or in the shiny surface of your polished car. These surfaces, in order to reflect light all in one direction, have to be very smooth. Otherwise, light would be scattered off of them. Even objects that appear smooth to our eyes, like this desk, or even to our fingers, at the microscopic level are not smooth enough to not scatter light, and that's why I can't see my reflection in this desk. The second type of reflection is diffuse reflection. Diffuse reflection is what happens when light is reflected off a surface, but in many different directions. So all the light that hits this desk is scattered by the rough microscopic surface of it into different directions, which means that light doesn't immediately come back to my eyes, and as a result, I can see the object, but I can't see an image of myself in the object. The last thing that can happen when a light hits an object is that it can be refracted. So this happens in translucent and transparent objects because some light has to pass through the object. And what happens is that when light changes what material it's traveling through, we already addressed the fact that it will change speed. And when it changes speed, then that beam of light bends. So refraction is said to be the bending of light. This is where our notes are going to end for today.